Hello, I'm Roman, and welcome back to the series of videos Neural Networks from Scratch in Golang, where we dive into the bare bones of neural networks, trying to understand how we can write them from the ground, and we're doing this in a Golang. And this is another video. In the previous one, we started, I think we checked half of the chapter 2 that is called Coding Our First Neuron, and today we'll continue from batching the data. To study these neural networks, I'm using these neural networks from scratch in Python book, but again, I'm writing everything in a Golang, as you can see, just to make things more complicated or more challenging for me. So let's go. I think I was surprised I received even the first comment on the first video about an alternative for NumPy for Go, and one person suggested to use Gonum, which I actually wanted to use. And we'll see, maybe we'll start using it today already, or we will continue as the book goes, and then we will see. But at some point we will need to go from, implementation of this stuff like the dot product, for example, into something already existing. So let's go. This is what we checked the last time, and okay, I will silent music a little bit. Okay, a batch of data. To train, neural networks tend to receive data in batches. So far, the example input data have been only one sample or one observation of various features called feature set. Here, the 1, 2, 3, 2.5, I think this is the input. Data somehow meaningful and descriptive to the output we desire. Okay, imagine each number as a value from a different tensor from the example in chapter 1, all simultaneously. Yeah, so for example, here we're using it as an input for the model itself, but we can treat it as an input from the previous set of the neurons, from the previous layer. Each of these values is a feature, observation, datum, and together they form a feature set instance, also called an observation, most commonly a sample. So this is a sample of the data with one-dimensional shape, or often neural networks expect to take in many samples at a time for two reasons. One reason is that it's faster to train in batches in parallel processing, and the other reason is that batches help with generalization during training. If you perform a step of the training process on one sample at a time, you're highly likely to keep feeding to that individual sample rather than slowly producing general tweaks to weights and biases to feed the entire dataset. I'm not sure I fully understand this, but okay. Feeding or training in batches gives you a high chance of making more meaningful changes to biases, weights and biases. For the concept of fitment in batches rather than one sample at a time, the following animation could help. Okay. Okay, so the idea, I guess, it has it's just jumping between the data. Okay. Wait. Okay, so this is the result. Okay. Batch size. Okay, so the intention that with a batch size of 32, the model, which is the green line, has better fit into the data. Example of linear equation fitting batches of 32 chosen samples. See animation below, blah, blah, blah. An example of batch of data could look like example of batch, its shape and its type. Okay, so we have 8 inputs and each of the size 4. So we have a 2-dimensional array or matrix. Okay. Recall that in Python and in our case, lists are useful containers for holding a sample as well as multiple samples that make a batch of an observation. Such an example of a batch of observation, each with its own sample look like. Well, okay, well, instead of the one input, we have a bunch of the inputs. This list at least could be made into an array since it's homologous. Note that each list in this larger list is a sample representing a feature set. So each one is a sample and also referred to as feature set instances or observations. We have a matrix of inputs and a matrix of weights. And we need to perform the dot products on them somehow, but how and what will be the result? In this example, we need to manage both matrices as a list of vectors and perform dot products on all of them in all combinations, resulting in a list of lists of outputs. A metric, this operation is called the matrix product. Okay. The matrix product is an operation in which we have two matrices, and by performing dot products of all combinations of rows from the first matrix and the columns of the second matrix, resulting in a matrix of those atomic. Okay. Okay. Okay, so instead of the multiplication, I mean, you treat every row and, I mean, the matrix product is a combination of the vector products. Perform a matrix product, the size of the second dimension of the left matrix must match the size of the first dimension of the right. Yeah, so they should. So if we should multiply the first row with the first column, they should have the same size. To elaborate, we can also show that we can perform the matrix matrix product on vectors. And because you can see a vector as a two-dimensional matrix. In one case, it will have, for example, 1 by 3. Here, in the second one, it will be 3 by 1. And it looks like, and this is the matrix product, and it results in a matrix size 1 by 1 with one number. If, for example, it will be 2 by 3 multiplied by 3 by 2, we would have in that case a matrix of 2 by 2. Product of a row and column vector results in a scalar. In other words, row and column vectors are matrices with one of their dimension being of a size of the one, and perform the matrix product on them dot product, which result in a matrix containing a single value. In this case, we performed a matrix multiplication of the matrices with the shape. Yeah, this is what I've been referring to. We can show, we can represent any vector as a two-dimensional or even three-dimensional with one dimension, with one size of a couple of dimensions. And the resulting array has the shape of 1, 1 or size 1, 1. Transposition of the matrix. How did we suddenly go from two vectors to row and column vectors? We use the relationship of the dot product and matrix product, saying that the dot product of the two vectors equals a matrix product of the row and the column vector. We also have temporarily used some simplification, not showing that column vector B is actually an transposed vector B. Yeah, how it was called, how it was shown in our university, you're doing transposition. The proper equation matching the dot product vectors A and B written as a matrix product should look like. So we have a vector A and a transposed vector B. This is why it comes from the horizontal into vertical. So it got transposed. So all of the values that were in the rows now placed in the columns. So for example, let's take a look at this example. So for example, we have this row 0, 1, 2, 3, 4, and once we transpose it, it should be 0, 1, 2, 3, and 4. Here's like this. Here we introduce one more new operation, transposition. Transposition simply modifies a matrix in a way that its rows become columns and columns become rows. I mean, it's not like the rotation, because, well, if you rotate, for example, the matrix, you will get very different things. This is exactly a transposition. Okay, yeah. Now we need to get back to row and column vector definitions and update them with what we just learned. We need to get back to row and column vector definition. Okay. A row vector is a matrix whose first dimension size, the number of rows, equals 1, and the second dimension size, the number of columns, equals n, the vector size. So like this. In other words, it's a 1 by n array of a shape 1n. With NumPy and with 3 values, we can define it as it is. So this is, you can see there is a double squares, meaning that it's a two-dimensional array with one element inside, which is a one-dimensional array of 3 values. Yeah, no the use of the double brackets here. To transform a list into a matrix containing a single row, we can put it into a list and create a NumPy array. But for example, if I would like to declare an opposite, it will be something like this: 2, 3. This will be the transposed, like the transposed vector b that we saw before, because it's a two-dimensional array with 3 elements, and each element is one-dimensional array of the size 1. So this is why we will have it as 3 by 1. We can put it into a list and create NumPy array. Well, this is what I will need to check. What I'm going to use for the Go. Okay, I need to stick to the microphone. And how I will create. But I think we will go through this chapter 2 and probably rewrite the neuron type with the Gonum. But let's see. Again, note that we encase A in the brackets before converting to an array in this case. Yeah, so you basically put a one-dimensional array into another array. We can turn it into one-dimensional array and expand dimension using one of the NumPy abilities. Yeah, this is where the NumPy's magic happens. So we can expand dimension. So this creates a one-dimensional array, and then we can expand its dimension. But column vector is a metric where the second dimension size equals 1. In other words, it's an array of n1. With NumPy, okay, we're not interested in this, but okay. Okay, maybe I actually need to try to implement this with a layer with a Gonum. Okay. I want to move it into another function just not to miss it. Okay, let's call it run model. And where's okay, now we need Gonum. Encourage to get okay, we edit. Go. Oh, yep. So this should be, I think, like this. Imported but not used. Okay. So now we need to find a way to create Gonum vector. Okay, now I need the started. And find the documentation. Okay. Empty matrix. Allocate a zeroed real matrix of size. function. Matrix. The matrix interface is defined by three function dims, which returns the dimension of the matrix, at which returns the element. Generate a 6x6 matrix of random values. Okay. For example, I want to, what's we have here? Okay, we have for example, we have A equals to 1, 2, 3, and we have B 2, 3, 4. Now I want to create the matrix. Mat. Mat. New dense. Okay, so the first one, row columns. Okay, so for the row, I will have 1, 3, and data. Okay, then I will have B, and I want performs an implicit transpose by returning the receiver inside the transpose. So it's implicit. So right now we should have one as the horizontal and one as the vertical, right? Okay. Interesting. Caps return the number of rows. Okay, in the backend matrix. Okay, let's take a look at teams. Okay, so by the dimensions we can see that it's transposed. And do we have the dots? Okay. That returns the sum of the element wise of the product A and B. Dot panics with arrow shape, the vector sizes are unequal. But will it work for me? Dots. Okay, maths dot. So it should be, well, AA And you so it cannot interesting. So the A is a tens. What is tens? Dense matrix representation. Can I? Terms and underline. Okay. Terms and metric. Okay, what I want to do, I want to have a dot product between, well, okay, product, dense product. Product calculates the product of the given factors and places the result in the receiver. The order of multiplication operation is optimized to minimize the number of floating point separation on the bias set all matrix multiplication. Okay, so there is a function called product. It takes matrices, right? No. Package math product. Oh, it's for the dense. Okay. We have this dense. Like this. So it's AA used. Product calculates the product of. Oh, it returns factors. Okay, yeah, it will be interesting. Okay, let's stick with the dot. Dot returns the sum of the element-wise products A and B. Okay, let's start from mad vector. What's the argument? The best description. The vector is a vector. Okay. Zero Horizontal test. Oh, it's type here. Okay. Gate 3. Oh. 1. Really? Product calculates the product of the given factors and places the result in the receiver. The order of multiplication, blah, blah, blah. Some dense. But matrix is not. T returns the transpose of the matrix. Whatever T returns a copy of the underlying. Okay, maths new math. Do I have functions? Dot. Okay. Dot works with two vectors. Okay. Some trace row log formatted. Formatted. Maybe context. Oh, int receiver. Okay, move takes the matrix. Okay, new dance. So I should have, okay, results, math, and new dance, and it should be 1, and I think it's if the data is nil, a new slice is allocated. Okay. Result declared. Okay, then we do this product, and right now I need to pass matrices. Okay. Print. Oh no. FMT prints len maths formatted results and dimension mismatch. Why? Not still. Dimension mismatch. New dance. No. I need to understand what this. It goes from math product. Okay. Dense arithmetic. Dense. Okay. Product calculates the product of a given factors and places the result into the receiver. The order of multiplication is optimized to minimize the number of floating points operations on the basis that all metrics. Let me test this. Dim. Okay. Let's take a look at the first one. So what terms R? Dim C. This is 3 and 1. Okay, with B. 1, 3. Then why it's a mismatch? Okay, maybe I need to do this. So not the vector dance, I need new dance. The first one is 1, 3. The second one is dance. This is 3 by 1. And I don't need the transpose. No, okay. Okay, so the issue was with the fact that I created the vector. Okay. So what we did, yeah, and it took me pretty long time, but still. So we used the Gonum to create the two matrices that will represent two vectors. Because they have, so these will be, you know, like, that's 1, 2, 3. And I would say it's like this. The second one is 2, 3, 4. Okay. We have achieved the same result as a dot product of the two vectors, but performed on the matrices and returning a matrix, exactly what we expected and wanted. It's worth mentioning that NumPy doesn't have a dedicated method for performing a matrix product. The dot product and matrix products are both implemented in a single method. Well, this is actually a difference for the Gonum, because from the documentation we saw that we have the dot function that takes two vectors and it returns the float, while the product takes several matrices. It's actually, it could be more, because it places the result into the receiving matrix, which you need to pre-allocate before. I think it uses put dense workspace. Interesting. Oh, I think this is where I had the panic. Reuse, copy, return. New multiplier. What is it? Something different. Result pair.multiply. Multiply works the optimal operation 3 found by optimize, blah blah blah. But multiply subchain. I'm curious to see if it actually uses the dot product inside, but looks like not. Okay. Okay. How long we are writing? Okay, 46 minutes. A layer of the neurons. I guess here we will actually use what we wrote. Let me take a look. Yes. This is already 40. Okay, I will start reading just to check, but I will continue. And I think we can... Well, okay, let's see. Let's see what we need to do, because I see that we need to have the inputs and the weights. And probably instead of running this, we will do something like this. So instead of defining the vectors, we'll define several matrices, and then we will use the dot product to get the results. Let's get back to our inputs and weights. When covering them, we mentioned that we need to perform dot product on all of the vectors that consist of both inputs and the weights. As we have just learned, that's the operation that the matrix product performs. We just need to perform transposition on it. Second argument, which is the weights matrix in our case. To turn the row vectors, it currently consists into the column vectors. I'm still trying to get inside it, my hand, okay. Yet. Initially, we were able to perform the dot product on the inputs and the weights without the transposition because the weights were a matrix, but the inputs were just a vector. Okay, so that's true. We had one input, one vector, and we had basically what we did here is we had a dot product between matrix of 1, 4 and 3, 4. No, 4, 3. Because we transpose it. Okay. When inputs become a batch of inputs, a matrix, we need to perform the matrix product. It takes all of the combinations of the rows from the left matrix and columns from the right matrix, performing the dot products on them and placing the results in an output array. Both arrays have the same shape, but to perform the matrix product, the shapes value from the index 1 of the first matrix and the index 0 of the second product must match. They don't right now. Okay, so this is the first input that we had before, right? And we had Okay, so what they're saying, so this is the first batch of the input, and this is actually, well, this one is the first neuron, this is the second neuron, and this is the third neuron. Like we did this. And in order to get the value, I think the value was 2.8. If we transpose the second array, values of each shape swap their position. That's true. Okay, so right now, with this one, we have the first input, the first neuron. If we multiply, let me just, I don't remember, run more. Okay, this is the results without the bias. It's just dot product, right? Let me check. So 2.8, this is the first one minus this minus, okay, this. Okay, so we have the first input, we have one neuron second neuron, third neuron, and it ends up into one row, 3 columns with the values, and this is it. So, okay, what we have. So this is the representation of our layer with 3 neurons. This is the first input, this is the result for the first input. And this is the second input, this is the result for the second input, and the same for the third. Okay. And yeah, and then we're multiplying the array of the biases, and here we see, oh, this is actually my result. Okay, so this is NumPy, and this is the end of... Okay, so I will stop for tomorrow, or I will stop for today, and I will leave the implementation of these for tomorrow. So tomorrow we'll start from implementation of the matrix product for the batches. We'll need to rewrite this, because right now we have 3 neurons and we need to convert them into the matrix. I mean, I will rewrite this code to look more like to look more like this. Yeah, but actually today we had a good results. I used the Gonum instead of the NumPy. I had to spend some time on this, but I managed to do this. But for now, I see you tomorrow. Bye-bye.